Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about the Hammond postulates. So what is Hammond postulates? You know my friends, the Hammond postulate states that the transition state of a reaction resembles the structure of the species, reactant or product to which it is closer in energy. The Hammond postulate relates reaction rate to stability. So we have here an exothermic reactions and endothermic reactions. You can see the pictorial diagram for endothermic reaction, reactant energy less than product energy, and this is the transition state. So transition state resembles the product more. These products, it is resembles more with the transition state. The transition state resembles the reactant more. You can see in exothermic reactions, the energy of reactant is higher than the energy of products. So it is resembles with the transition state more than the products. So transition states in endothermic reactions resembles the products. The transition states in exothermic reaction resembles the reactant. So transition state energy of an endothermic reaction, you can see endothermic reaction energy increases. Here is the difference between transition state. The lower energy transition state leads to the lower energy product. Here product, the reactants, and these are the products. So slower reactions and faster reaction coordinate. Now transition state energy of an exothermic reaction. Exothermic reaction, you can see this is energy increases. This is the reactants, transition state, and the difference in this energy is activation energy is similar to that both pathway. This is the activation energy and this is the differences of the energy of products. So decrease the energy of product has little effect on energy of transition state. Now application of Hammond postulate to the Sn1 reactions. Since methyl cation is less stable than trimethyl carbon cations, so activation energy 1 is greater than activation energy 2. The reaction 1 is slower. So you can see here the activation energy 2 and this is the energy. The activation energy 1 and this is the energy. So trimethyl carbocations more stable, means 3 degree carbocation more stable carbocation than this 2 less stable carbocation. So less stable transition state and more stable transition state. Why? The energy is less of E2 with respect to E1. Now predicting the mechanism of nucleophilic substitution reactions. 4 factors are relevant in predicting whether a given reaction is likely to proceed by an Sn1 or an Sn2 mechanism. First, the alkyl halide, methyl halide, and second, the tertiary like this. Second, the nucleophile, strong or weak, living group, good or poor, and the solvent, protic or aprotic. Nature of alkyl halides. The most important factor is the identity of alkyl halide. Increasing alkyl substitution favor Sn1. Decreasing alkyl substitution favor Sn2. So you can see here methyl Sn2, both Sn1 and Sn2, 2 degree and 3 degree Sn1. Increasing rate of Sn1 reaction. Increasing rate of the Sn2 reaction. So methyl and 1 degree halides undergo Sn2 reaction only. 3 degree alkyl halides undergo Sn1 reaction only. 2 degree alkyl halides undergo both Sn1 and Sn2 reaction. Other factors determine the mechanisms. Now vinyl and aryl halides. Sn1 or Sn2 reaction occurs on sp3 hybridized carbon. Vinyl and aryl halides which have a halogen attached to sp2 hybridized carbon do not undergo Sn1 or Sn2 reactions. Heterolysis of the CX bond would form a highly unstable vinyl or aryl cation. So vinyl halides, phenyl halides or aryl halides. You can see here sp hybridized after breaking of this carbon and Br bonds, Br minus and carbon positive charge, a vinyl carbocation highly unstable. Effect of nucleophile. Strong nucleophiles which usually bear a negative charge present in high concentration favor Sn2 reaction. Weak nucleophiles such as water and alcohol favor Sn1 reaction by decreasing the rate of any competing Sn2 reaction. Considering what happens when 2-degree alkyl halide A, which can react by either mechanism, is treated with either the strong nucleophile OH minus or weak nucleophile water. So you can see cis-1 bromo 4-methyl cyclohexane, strong nucleophile and weak nucleophile. Now predicting Sn1 and Sn2 reactions. The strong nucleophile favor an Sn2 reaction, you can see here. Weak nucleophile favor an Sn1 reactions, you can see here. This bond breaking, formation of planar carbocations, now water as a nucleophile attack on the center, then we are again trapping this proton and shifting of this bond as a lone pair of electrons and formation of this cis and trans isomers. So the nucleophile attack from above and below. Now effect of leaving groups. A better leaving group increases the rate of both Sn1 and Sn2 reaction. Transition state of Sn2 mechanism and transition state of rate determining step of Sn1 mechanisms. So you can see nucleophile carbon X. So a better leaving group is more able to accept the negative charge. So you have RF, you have RCl, you have RBr, you have Ri. Increasing leaving groups ability, increasing rate of Sn1 and Sn2 reaction. Now effect of solvent. Polar protic solvent like water and alcohol favor Sn1 reaction because the ionic intermediates both cation and anion are stabilized by solvation. Polar aprotic solvent favor Sn2 reactions because nucleophiles are not well solvated and therefore are more nucleophilic. Now predicting Sn1 and Sn2 summary. You go through this table summary of factors that determine the Sn1 and Sn2 mechanism. So Sn2, this alkyl halide favored by a strong nucleophile, usually a net negative charge, and another factor for favoring these conditions, polar aprotic solvent. And this is going through Sn1 favored by weak nucleophiles, usually neutrals, and polar protic solvent. And this 2-degree is favored by Sn1 and Sn2 both. The mechanism depends on the conditions. A strong nucleophile favors the Sn2 mechanism over the Sn1 mechanism. For example, alkoxide is a stronger nucleophile than the alcohol. So, alkoxide favors the Sn2 reactions and alcohol favors the Sn1 reactions. Now, protic solvent favors the Sn1 mechanism and aprotic solvent favors the Sn2 mechanism. For example, water and methanol are polar protic solvent that favor the Sn1 mechanism, whereas acetone and DMSO are polar aprotic solvent that favor the Sn2 mechanism. Now, organic synthesis. What is organic synthesis? It is a systematic preparation of compound from a readily available starting material by one or many steps. Nucleophilic substitution reaction, especially Sn2, are used to introduce a wide variety of functional groups into a molecule depends on the nucleophiles. Organic synthesis has produced many useful compounds, for example, pharmaceuticals, pesticides, and polymers used in everyday life. Chemicals may rely on synthesis to prepare useful substances such as in natural products produced by organism, but in only minute amounts, like Taxol used in cancer treatments. So organic synthesis using alkyl halides You can see formation of alcohol, ether, ester, nitrile, alkyne, azide, amine, thiol, sulfides. Now retrosynthesis, thinking backward in organic synthesis. This is known as retrosynthesis. So to carry out the synthesis of particular compound, we must think backward and ask ourselves the questions: what starting material and reagents are needed to make it? So if a nucleophile substitution is being used, determine what alkyl halide and what nucleophile can be used to form a specific product. So you can see this is what is the starting material and what is Rx, and this is indicating what reagent is needed, what is the nucleophile, and this is the synthesized this products. This is urea. So friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.